But we know that every rule for derivatives, there's a counter rule for integrals, right? I can go forwards and backwards, right? And we looked at the substitution rule, and that corresponded to the chain rule when I took derivatives. So substitution, work backwards. For integrals, I could do the chain rule and work forwards. And that's a great way to check it. There is an integration rule that corresponds to the product rule. So when I have two functions being multiplied together, if you've seen any of those, you're probably wondering, well, how am I going to do that? And up to this point, you might have just multiplied the two together, and then whatever you got, you did the integral of that. Probably just multiply them together and do the integral. But I'm going to show you the way to work backwards, take the integral of two functions. Problem is, you got to find the two functions. What are the two functions? So this is the product rule, right? If I took the derivative of two functions being multiplied, I do first derivative of the second plus the second derivative of the first, right? That's the product. Well, I got all this proof here. If you want to spend time looking at it, it's on Canvas. Yada, yada, yada. So it leads me down to this. So because, so since this is true up here, the product rule, I have this down here. The integral of u dv. I don't want to put x in there because I'm going to change it. Integral of u dv. So here's the challenge. I got to figure out what in that integral am I going to call u, and then what am I going to call dv. U is going to be one function, and dv is going to be the derivative of the second function. So that's the challenge here, is to find the two functions. So which part, and you know, once we go through a couple of them, you'll see. But I need to pull out, I'm going to get an integral of something, and if you want to try this method, you need to make part of the integral u and part of it dv. And then this is how I can take the integral of this thing that I've divided into u dv. It'll be u times v minus the integral of v du. So I'll have to take the integral. So the integral of this thing is going to be u times v. Well, we'll figure out what u and v are. Minus, oh, here's where the integral comes in. Integral of v du. The opposite of what I've got right there. The whole purpose of this is to try to get your integral to be something simpler than what's staring at you. So we want to obtain a simpler integral than the one we started with. So we're going to try to choose u to be a function that becomes much simpler when I take the derivative of it. If I'm taking the integral of something that has a power to it, we can often use this method to reduce the power. So it's going to help me make things a little easier. And of course, you can always check your answer by doing the product rule. When you get your answer, you do the product rule and see if you get the integral or the integrand. Okay. If we have a definite integral, I got to do this. I'm going to have to plug it. So I've got f and g here instead of u and v. So this is like u dv, and there's u and v, right? U times v. So I still have to plug in the intervals of integration. Minus, well, here's where the integral is going to come in. Of course I would do it there, but you might forget to do it here. And if we don't have an indefinite integral, don't forget to, don't do LeBron James and forget the plus c. That would be embarrassing. make sure the hole's full now. Okay. Deeper. So, here it is. Probably should put plus just to remember this. Just to remember. And then if it's a definite integral, don't forget to plug in your intervals of integration. There's two parts here. Sometimes we forget that. Okay, I say we practice it. Who's ready to practice? Bless you. Or should I say Gesundheit? Okay. Let's see. Didn't leave very much room to work this time. The integral of x sine x dx. Let's use integration by parts.
So is that the integral of,
I'm going to need to figure out what's u and what's dv. And let's see, you know, sometimes you have to try, maybe I'll let this be u and that be dv. Maybe I want this to be u and that to be dv. Maybe you have to move them around.
dv is the easier part, right?
Is it what?
The easier part?
Yeah. Well,
The,
I would let this be u and this be dv.
and why exactly?
Because when I take the derivative of u, I'm gonna get 1. I get something real simple, real simple. In fact, I'll write this over here. I'm gonna let u be x, and then du will be 1 dx. 1 dx, or just dx. And then if dv is this thing, which if I've got sine or cosine, it's real easy to figure out the integral of that, or the antiderivative of that. So if I let dv be sine x dx, so those are the things I gotta come up with. Then what's the antiderivative working backwards? What would b have to be? Negative cosine. Yeah, negative cosine. So if I let a derivative be sine or cosine, it's pretty easy to figure out what the antiderivative is. And I want to make that easier. If I let that be sine x and that was cosine x, I don't know if that would be easier. It's just kind of maybe changing the way it looks. But I want to try to make u look easier. So, hey, I want to take the integral of this now. U dv. According to the formula, I need u times v minus the integral, the opposite of that, v. My v's and u's are probably on u. So now let's just plug in the pieces. So that's going to be u was x and dv, or v, sorry, minus cosine x, minus the integral of v, which was negative cosine x, du dx. So just plug in your pieces. So that's my process. Let's see, I'm gonna get just whatever this is, the integral part comes in the second part. So I've got negative x cosine x. Hey, what's the integral of, I can pull the negative out, right? What's the integral of cosine x?
Negative side? Sine.
Sine x. Cosine x.
Oh, wrong direction.
And I pull the negative out. And plus c. There's the integral. Sometimes it can work if you let the other thing be, you know, you enter, I let U be that. And sometimes it'll work if you let V be that. Sometimes it works both ways. And sometimes you plug it in and you go, this is not simpler. And then, okay, well then go back and try it the other way. This is integration by parts, which is the counter to. Should we do it again?
Yeah.
Any questions on this? It is kind of a trial and error. We're getting to higher level integrals if we're doing the reverse of the power rule, so it doesn't mean you're gonna get the right answer the first time. It's kind of a trial and error thing. Maybe we'll do 3 today. I don't wanna do them all, so UV misses out. Let's see, I've got the integral of the natural log of x dx. Why do I have to take the derivative of to get natural log of x? I could try u substitution. I could try that. We know this is integration by parts, so maybe I want to find u dv. So I know if I take the derivative of ln x, I don't get ln x. I get 1 over x. That's kind of probably pretty easy. So let's let that be u. And I take du. I get 1 over x dx. Oops, I forgot to put this back, dx. I said dx, I forgot. Or dx over x, whatever you want. So that's over here. And then I gotta find the dv. There's only one thing left, and that's dx. So that's the other thing. So what's the integral of just 1 dx? Just x. And now if I want to plug everything in again, I'm gonna write down the formula again. Well, sorry, that's dv. We call that dv. So integral of u dv is gonna equal u times v minus the integral, the opposite of that, v du. Just plug things in. Let's see, u is the natural log of x. V is x. Is it okay if I put that up front? Otherwise it looks like the natural log of x squared. So I'll put the v up front. Minus the integral. Here's where I really have to take the integral of v is x. And du is 1 over x dx. So that's going to give me x ln x. X over x, that's just 1 minus the integral of, I'll put that in there. That's just 1 dx. So you don't have to take the integral of that. We just said, what's the integral of 1? X minus x? 2.
Do you need to do that whole process?
Do what?
Do you need to do that whole process?
Like all of this?
No.
No. I'm just doing it because this is the first time we've seen it.
No, no,
Um,
like, because the rules I show you, you just know the answer, like,
That's fine.
if they put you that, you just can use right
That's
answer.
fine.
Okay.
Yeah. I'm just teaching this, so I'm showing
But in
the
AB
parts we're using.
But in the AP, they say, like, show the process, and you just know the answer. Because there's a rule that says the answer.
I don't know if they're gonna say that for something like this. I don't think so.
Does the C for the integral always have to be capital?
Good question. I've just always considered my C, maybe because I'm stressing it to make, but I wouldn't think so. Because little c, lowercase c means constant. Yeah. So I wouldn't think so. Okay. So the challenge on this is gonna be trying to figure out what's U, what's dV. And you are gonna want U to, when you take the derivative of whatever you decide U is, you do want it to come out to be simpler than what it is right now. So maybe we'll do number 3 and we'll wait on 4. Man, I tried substitution, that ain't gonna work. I can't get rid of that. Or I can't get rid of that. So I might try, let's see, if I let this be U, the derivative of that is the same thing. I don't know if I made it simpler. If I let that be U, the derivative of that is 2x. Oh, I mentioned something about using it for powers because I can reduce the power. That might be a good thing. So I might let that be U. Then the rest will be dV. Let's see if that works.
Would you ever use dV for something with a power?
Yeah. I mean, it is here. E to the x is.
I mean, not like squares.
Yeah, you could. If the other part was probably even more
Yeah,
complicated.
okay.
Yeah.
But usually not. You try to reduce the power and.
I would try to get the U part simpler. Yeah.
But even if you switch them, you can still solve it, right?
We can try.
No, I'm just asking.
Did
Like,
you? Sometimes you can, and sometimes it gets more complicated when you switch them.
But it's.
You took a
possible.
problem, and instead of making it
But when it's
simpler, you
possible.
made it more complicated. Sometimes you can,
Okay.
yeah.
Yeah.
Sometimes you can in a more simple way. You can still do it, but you may have made the problem more challenging for you. And we're trying to make it easier for you. So I'm gonna let U be x squared. I'm gonna let dV be the other part, which is e to the x. Then I need to find U, and then I need to find V. Well, V's pretty easy, right? That's just gonna be e to the x. And that's pretty easy. 2x to the 1 dx. Oh, kids. And now, you know, I am gonna show every little piece because so it's gonna be U dV. You know, if they were to only turn their heads and look in this room, they would realize what's going on in the school under their very nose. Under their very nose. Okay, minus the integral of exactly the opposite of ED. Now I just have to fill in the pieces and see if it works. Oh wait, these are the two I thought. So I've got x squared e to the x. Minus the integral. See, I don't have to do anything with that. That's already done. So I just have to take the integral of this other part. B e to the x du 2x dx. Which I can bring the 2 out, right? So that's going to give me x squared dx, e to the x, sorry, x squared e to the x. I'll bring the 2 out, and just take the integral of e to the x, e to the x, dx. What do I do here?
Do you do the same thing now for x to the x times e to the x?
Maybe I could. Huh? Do it again? Okay. So I got this part. And you're saying do this again. Oh, maybe I'll let that one be u and this one be dv. Because when I take the derivative of x, I'm just gonna get 1. Can't get much simpler than that. So, u equals x, du equals 1 dx. And dv would be e to the x dx. You see that? I'm getting off of this. And v would be just so if I'm doing it again, this becomes u, here I'll write it down, u times v minus the integral, this time of v, which I got this part, don't have to do anything there, minus 2 times. Now I gotta plug in again. X times e to the x. Minus the integral of b e to the x du is just dx. That's the beauty of when you let u be something with a power and then you take du, the power reduces by 1. If you got to do it again, eventually you're going to get it down to nothing. Okay. So, let's see what we got here. We got x squared e to the x. Don't have to do anything there. We got minus 2 x e to the x. And we've got minus a minus plus e to the x is the integral of that plus. Oh. Did I miss anything? Oh, yes, I did miss something. Sorry. 2 times that, I got 2 times that. I did the minus minus plus 2 times that. I got 2. Sorry. So sorry. Forgot. Could we factor something out? Is it worth it? That's the right answer, right? Maybe I can factor an e to the x out. Is that simpler? I don't know. What I'm saying is, what if I wrote it like this? Is this any simpler? Well, you could actually, let's see. I don't know, is that simpler than that? I don't know. Kinda looks the same to me.
Why did you write the plus c?
Yeah, which write the plus c.
Well, it doesn't matter, if I pull whatever this is out of the plus C2, it's still a constant. And I don't know what the constant is, it could be 7, it could be 1,000,000, it could be negative 2,000, I don't know. It's still gonna be a constant. If you left it outside, it's the same. Like if you just left that answer, it's fine. You couldn't leave that answer because you still have to do that. But if you got here, you're good. I just didn't know. I don't know. They both look about the same. I don't think one looks simpler than the other. Either or. Let me put that up here. For Evie.
But if you multiply that bottom out, it would say c times c e to the x. And that doesn't matter?
No. It's still gonna be a constant. No, it doesn't matter. I mean, if that bugs you, we'll do this.
No, I'm just asking.
I mean, either way, I probably would just, I mean, I did in my notes, I just stopped there. you wanna factor out what they have, that's fine. The problem is, you know, if you go further than you need to, you risk the error of an arithmetic error or something. So I would just really just say. That's good for today, right? Why don't we need to know this instead of trig substitution? I'd rather, this to me is, I don't know, 20 times more helpful than trig substitution. But yet, you don't need to know this. But you can use it now that you